Hi everyone, and welcome to our video on rates of change. So a rate of change is something per something, like miles per hour. And you might see that one like mph, miles per hour, or feet per second. So these are involving velocities, or it's really anything per anything, like dollars per month. Or like in sports, maybe like points per game. Okay, so all of these are a rate of change. They are all something per something. All right, and so the rate of change is what will be directly important to us when we're looking at our next things in calculus. So to get started, we're going to look at what's called an average rate of change, and we'll start that off with the average velocity. So in this example, it says, I drove to Dallas from College Station and recorded my distance traveled in miles every 0.5 hours in the table. Okay, so we have our time, which is our x, and then we have our distance function, which would be f of x, and then we have our data here. All right, and then it asks, what was my trip's average velocity? Well, to know average velocity, average velocity, we're going to usually denote that as v with little av. So like little average velocity. It's just one notation, but I'm going to use it like this. Okay, so our average velocity, well, our average velocity in physics, let's just put it down here, would be, okay, so we have like miles per hour. That's a distance over a time. Okay, so in this problem, let's go ahead and break it down. I'm going to do equals. Let's leave a little space. I'm going to come back to this space for a reason. But if we're looking at the average velocity over the entire trip, well, it looks like I started at a distance of 0 and I traveled a total of 190 miles. So we have 190, and then that would be miles, just to put the units for now, divided by however long we drove for. Okay, so it says 3 right there. And then I'm just going to use my calculator here because we probably wouldn't say 193rds. And I will put my unit 2 in a second, but let's go ahead and do that division. So we're going about 63.33 miles, and this was in hours. So this simplifies to be 63.33 to 2 decimals miles per hour. So notice the units are still just getting divided. Miles divided by hours is miles per hour. Okay, and the numbers also got divided to change it to a decimal. Okay, so that's our average velocity over the entire trip. All right, and we'll come back again. I left that space there for a reason. Well, let's look at number 2 before we fill in that space. So what was my average speed during the between 1.5 and 2 hours? All right, so our average speed, which we will just say is velocity in this case. So our average velocity, again, I'm going to leave a little blank here. Well, we want to figure out the time and the distance traveled. Okay, so let's deal with the time first. So the time it takes to go from 1.5 to 2, well, we could do that in our head. It's a mental thing. That's really just 0.5 hours. So that's the amount of time that was counted in between 1.5 and 2 hours. And then we need to see the distance traveled. Okay, so let's go back to why I have this blank. So notice I'm just going to subtract the 2 and the 1.5. So that's our times getting subtracted to show how much time had passed. And then we wanted to see how much distance had traveled. Okay, so well, from 1.5 to 2, we ended at 130. We started at 90, so that is a quick subtraction as well. That's 40, but we could see, hey, we could have just subtracted that also. 130 minus 90, like that, is our setup for the subtraction. And then, well, this time around, I can do this one without a calculator, but if you need to, go ahead and do it. It would equal 80 miles per hour. And notice I didn't put the units this time. I just wanted to say, hey, if I'm dealing with speeds, I know in this problem our units will be miles per hour. So we do usually want to put them at the end at least. I wanted to show them in this one just to show that they do get divided, and that's why it's the miles per hour. Okay, so that was our average speed. And so, well, what we did on this one, let's go back. So this blank space. So here I still did subtraction. It was the 190 minus 0 though. And then we also did subtraction with the time, 3 hours minus 0. So notice it's just taking our second value minus the first value. Well, the notation for this might be written as, if we're using our f of x and x's, we might say, hey, this was like our second value. Let me mark my x2 here like that. So this was our second x value, and this was our first x value. So we might say that this 3 was the same as doing x2, and then the 0 is minusing that x1. And then we also had our y value, so I wanted to do those second. So this is our second y value, y2, and this was our first y value, y1. So this was y2 minus y1 with that 0. Well, this might ring a bell just if we isolate this blue. So we see the average velocity, if we use these variables, is the same thing as y2 minus y1 over x2 minus x1. Well, that's really just the slope. That's the slope formula. M is y2 minus y1 over x2 minus x1. So notice that, so what we've got from this is that an average rate of change, and in this case an average velocity, is the slope. So we'll make that note in just a second, or if you're looking down at the paper you might see it. But the other way that we might see this as well, so with this, let me make my arrows again. Let's do it in red. So I have different starting times. So our x2 in this case is the 2. Our x1 in this case is the 1.5. So this is our x2 and this is our x1. So that's those two getting subtracted. Now instead of saying my y coordinates, how about I use my f of x? So to get my second y coordinate, I would have plugged the x little 2 into my function. So this is really f of x little 2, and this would have been f of x little 1, just to show it in a different way. So instead of y's, I'm using it like this. Okay, so again, we've got this average velocity is written in this formula way as f of x2 minus f of x1 over x2 minus x1. And again, that's really just the slope. Okay, so we see that we have the connection. So here's just the difference of preference between y's and f of x's. Okay, anyway, so this was our case for velocity. So velocity is an easy one that usually comes along with physics or in calculus. So it's kind of where it got started with our Newton's apple, but so we'll use it kind of frequently, but we also will get our business ones in as well. Okay, so let's use some of this vocabulary. So what we just found was the average rate of change. We did the average rate of change. So velocity is the average rate of change of distance over time. So let's go ahead and mark that too one last time. Our average velocity is, okay, so average rate of change, it's the rate of change of the distance. So change in distance over the change in time. So that's how it could be written in words as well. So that average rate of change, so velocity is an average rate of change, it's just a specific average rate of change. Okay, so we have an average rate of change, and we also have what's called the secant line. Well, the average rate of change, which we'll often abbreviate AROC, like as seen right there, measures an average change in a function from x equals a to x equals b. So just like what we did on this. So what they used in this is one more form with the different letters. We could have also said it's the same as the ones that we wrote. So f of x2 minus f of x1. So over x2 minus x1 is the same formula. They're just using x equals a to x equals b. It's just like saying from x equals x1 to x equals x2. So I wanted to show all the different notations. And then I wrote equals because, well, again, we could say, hey, it's really just, if we want to rewrite it using our most basic slope equation, there we go. So the average rate of change, again, is really just the slope. Okay, and then a secant line is a line that goes through 2 points of a function that has the slope that is equal to the average rate of change. So there's a space here because, so in this one, we did have some function and it's based on points, and we could plot it and do all that and make a graph. But what I want to do is just a quick one. So sometimes we have functions that maybe are curvy. Okay, so maybe it's something like that. And we want to know the average rate of change from maybe like about here to about here. And so we can find the slope through that point, or through the 2 points. Right there. There's my line through it. And then let me just draw my... So that's supposed to be a right triangle. So here we could say we've got our rise over run even. Okay, so but our average rate of change is the rise over the run in this case, so one other variation. And then we have a line going through these 2 points that represents the secant line. Okay, so we see that, so it would have the average rate of change as the slope, and then we have our secant line just going through those 2 points. Okay, so that's what it is abstractly, and that's what we'll start with, but we'll start to see some more applications for it in a little bit. Okay, so in example 2, it says let f of x equal this function. We're going to find the average rate of change of the function over the interval -2, 5. Okay, so what they're saying here is this, I'm going to use, this is my x1. That's that -2, and this is my x2. So I'm going to use my x1 and x2 styles. And so if they ever want the average rate of change, I'm just going to go ahead and instantly write out my preferred formula. I'm going to use the one with f of x2 minus f of x1 over x2 minus x1 for this case. Okay, so based on these values that I'm using, that's how I want to write this formula. Okay, you could choose a different formula if you prefer. They should all give you the same answer. Okay, and so with this problem, the denominator's no big deal. We have those. So x2 is 5 minus x1, which is -2. Be careful, it's a negative, so it is minus a negative. So this will eventually become a positive. Okay, and then f of x2 minus f of x1. Well, we have our function here, so all we have to do is just evaluate those. So f of x2 is equal to, well, they say x2 is 5, so let's just plug that in. So all I want to do is f of 5, and they have that function right here. I can just plug in the 5 into those x's. So I'd have 5 cubed minus 2 times 5. And then from there, we'll just simplify. 5 cubed is 125. 2 times 5 is 10, so 125 minus 10 is 115. Okay, so what I have in the blue parentheses is that f of x2. And then we have minus, I'm going to put it in red parentheses, our f of x1. So I'm just going to do that down below as our scratch work. F of x1 is equal to, okay, so use the x1 value, which is -2. And then we'll plug it into our function. So I'm just changing those x's into -2's. So I have -2 cubed minus 2 times -2. And then now I can simplify. -2 cubed is -8. -2 times -2 is +4. So we have this becomes -4 once it's simplified. Okay, and then that can go right there. Okay, so there we go. And then now it's just order of operations, and you could use your calculator to help as well if it's allowed here. So we've got 115. This is really +4, so I'm going to write that as 119. And then 5 plus 2 really is 7. And then 119 divided by 7, I'm going to use my calculator for this arithmetic just to speed it up. So 119 divided by 7 is 17. Okay, so that's it. That's what we wanted. Okay, and what we have here, so this graph, I'm not sure exactly how it looks just by looking at it, or just looking at the function real quick. I know some things. I know it's something like this at least. Okay, so I'm gonna sketch something. I don't know, something like this. Okay, so probably not exactly like this. Okay, but something like this, and we could plug it into a calculator to get the real thing, but all I wanted to do is show a real quick thing about it. So at -2, so that's our kind of our red. So when we plug -2, that's an x-coordinate. So that's an x-coordinate, and we got this as a y-coordinate. So that means we'll say it's down here somewhere. And then our x2, x2, we had a 5 as our x-coordinate and 115 as our y-coordinate. So it's way up high. So let me mark that. So that's 5 comma 115. And then the red was -2, -4. So these still represent points if we want to look at them like that. Okay, anyway, so all we have here, let me do it in a green. If I were to connect these two dots with a line, this would be our secant line. And it has a slope of 17. So it has that slope is 17 because that's the average rate of change. Okay, which right now, again, is just abstract. It's just letting you know the average rate of change of a function. Again, if it's based on some type of application, it could be like miles per hour. It could be dollars per month. Okay, so it just depends on the scenario. We probably wouldn't have -2 as an x-coordinate involved if it was an application, but you know, it's still good practice. All right, anyway, so that's the abstract, or we have an abstract one here. Okay, let's do one more kind of abstract one, and then we'll see a word problem. Okay, so in example 3, we're let g of x equal 2 over x minus 1. Let's find the average rate of change of the function over the interval 2 comma 10. Okay, this time around, I'm going to use the a and b. So let's say that this is a is 2, and then our b is 10. Okay, so just to use a different formula, so just to show it really doesn't matter, it's just a different way that we could write it. So the average rate of change, here I'm going to do the f of b minus the f of a over b minus a. Okay, so these are still x values, we're just using a different form. And then from here, again, I'm going to just put in the denominator. So I have b is 10, a is 2, so I have 10 minus 2. And then we still need to find these like we did the last problem. Okay, so I want to find f of b, which is really f of 10. And so I used f, so I guess, oops. So that's what can be annoying sometimes about math. This is g, though, in our problem. So that means I should really change these into g's. Okay, so my fault, I forgot to look up. It's not a big deal really if we leave them as f's. We kind of would understand that it was really g, but I'm going to erase those. So sorry if you were using ink to make it match the letter that we had in our problem. Okay, so just I changed them to g's. Okay, so the f is generic, but sometimes it changes. Okay, anyway, so I am going to just plug it into my equation. I have 2 over 10 minus 1, which would give me 2 over 9. Okay, so that means I have 2/9 right there. And then we'll have to minus. Let's do that one in red. So minus, and then I want to find g of a, which is plugging in 2. We already did 10. 2 into our function, which gives us 2 over 2 minus 1. 2 over 2 minus 1 would be 2 over 1, which is really just 2. There we go. Okay, and if you have a calculator and if we're allowed to use it, all right, we could just plug it all in. I'm going to simplify this a little bit. So I have 2/9 minus 2 over 10 minus 2 is 8, like that. And then I'm going to use my strategy that we saw from limits a while ago. So, and actually I could put a 1 under that too if I'd still prefer. So I could have kept it as 2 over 1. The reason for that is I see my small denominator is 9. So if I'm doing this without any type of calculator, I'm going to multiply everything by 9. In the top it distributes. So I'll have 2. So 2 times 9 divided by 9. That means the 9s would just cancel. And I'm left with just 2. And then I have minus 2 times 9 would be 18. And then down below, I have 8 times 9 is 72. And so it looks like it would continue simplifying to be negative 16 over 72. And then however way we would want to simplify this, I think both of these are divisible by 8. So we would get negative 2/9. Okay, so that's our average rate of change. I guess I should just box it. That is our average rate of change. Now, again, you could use a calculator if you want. I'm going to pull it up real quick just to show how you could enter it into. Okay, here's Google's, but instead, let me just go to Desmos. Okay, and I'm going to use the scientific calculator so I can plug it all in. Okay, so if I want to simplify this, I can plug it all in. So 2/9. So I have, let's do 2 parentheses. 2 divided by 9. Oops. Sometimes we need to use the arrow. There we go. And then I want a minus 2. So I put the first parenthesis there. So I'd have this big thing divided by 10 minus 2. I guess, I could just do 8, really. 10 minus 2 is 8. And then there we go. And then here I can click it into its fraction, which is negative 2/9, which is what we had. Okay, so again, you could plug it in if needed. I think Desmos is a good one. It's quick and easy to find. It works just like a handheld one. Okay, anyways, so that's that. So we got it. Okay, and then afterwards it wants to find the equation of a line, of the secant line. Well, the main thing really is when you find the equation of a line is the main focus, I would say. The equation of a line, so whenever you see, let me just put it in words, find the equation of a line, of any line, so this happens to be a secant line, that's okay. I would use the old formula that is from our line equations from the past. It's our y minus y1 equals m times x minus x1. Okay, and with this problem, I guess our x1, so that's why I like the x1 and y1, or the x1, x2, and y1, y2, and the f of x2 and f of x1 a little better because it uses it in other formulas. Okay, but that would mean if my a is 2, that is the same thing as saying x1 is 2. Okay, so let's start to plug that in. I'm going to do y minus, and let's leave a blank. M is the average rate of change, which is that negative 2/9 that we found. So we'll plug that in right here. So we have negative 2/9. And then x minus, we said x1 is just 2. So it looks like this so far. And then y1, well, what do we get for y when we plugged in 2? Well, coincidentally, it is the same value. It is also 2. It's right there. So this one right here was our y1. Okay, because again, this 2 was our x1. So when we plugged x1 in, we got our y1 as 2. Okay, anyway, so I'm going to plug that in now. So I have y minus 2 equals negative 2/9 x minus 2. And then, well, what they would want is we would usually want it in this form, y equals mx plus b. That's the slope-intercept form. Form of a line. So that's usually what they want. So that just means we need to solve for y in this equation eventually. So first thing then is to distribute the negative 2/9. So we'd have y minus 2 equals negative 2/9 x. Negative 2/9 times the negative 2 would change it to a positive. 2 times 2 is 4, and then the 9 is still down by itself. And then last, I would need to add 2 to both sides. Well, adding 2 to both sides, I would need to get a common denominator. So I've got y equals negative 2/9 x. 4/9 plus 2. Again, I could use a calculator, or when I do plus 2, I know that that's the same thing as 18/9, because 18 divided by 9 is 2. So 4 plus 18 is 22. And then still over 9. And then that's it. There we go. Okay, so that is the equation of line through this. Okay, so again, we have some weird kind of scenario here. We could graph it just to show it. And, you know, I might as well. Let's do that real quick. So our math tools, let me go to the graphing calculator. I'm going to graph this function. So I'm going to do the y equals 2 divided by x minus 1. And then let's graph our equation there. So the negative, let's do it in another line. So we have y equals negative 2 divided by 9 x plus 22 divided by 9. All right, so here's our graph. And then I know it's nothing really special, but just to show, so here's the 2, 2. So that was our x1, y1. And then here is the 10 and the 0.22. That was our x2, y2, or our b, and then our g of b. So the 2/9 is 0.222. Okay, and so this line is going through the 2 points that we had, and it also has the slope of the average rate of change. Okay, so all this is doing is just it tells you the average rate of change of how this function is changing. So right now it's just kind of slowly going down at this point from this point. So from 2 to 10, it's got a slow slope toward that point. So if we had changed the point, if we were closer to like 0.5 or whatever, then we'd see it be very steep. So we'd have a steep slope. So it's just telling you how much the function changes, which is based on really looking at a slope. Okay, so this one's slowly going down from the 2 points. Again, if we had a point way up here, it would say it's going down fast. So the change is fast. Okay, so this is a slow change. Okay, anyway, so that's still just abstract for now. Okay, anyway, let's do one other. Let's do this word problem where it says if $5,000 is invested into an account that pays 1.2% interest compounded continuously, the total amount A of t in the account after t years is this equation. So notice it used the 5,000 right there. 1.2 got changed into a decimal. Okay, so it's just this is our compounded continuous equation where, let me go ahead and just write that too as a side note just in case we need it. For other things, compounded continuously is often A equals PERT, where A is the amount, we'll say future amount. P is the principal or the present amount. E is our special number, the 2.718, so forth. R is the rate, the interest rate. So R is interest rate, but it's just converted into a decimal. Convert into decimal. Okay, so in this equation it's 0.012, and then T would be time. Okay, so just in case we need it, it's a nice formula. It's not very complicated. It's used in other things as well. So like populations, how fast is a population growing, the spread of a virus or something like that, or even the decay of a population or the decay of like a virus. Say there's like a forest fire and the trees are burning. This could model how fast the trees are going down. Okay, so it could be used in other, so it does growth and decay. Okay, anyway, but right now we're doing money. All right, so they told us the formula. So A of t equals this, and they want us to find the average rate of change per year of the total amounts in the account for the first 10 years of the investment. Okay, so for the first 10 years, that would mean our T1 would begin at 0, and then our T2 is the end of the 10 years, 10. And so our average rate of change, so our AROC, well, they used A in this case instead of f of x, and we're using t's instead of x's, so I'm going to use A of T2 minus A of T1 over T2 minus T1. And then we could set it all up. Well, the T2 minus T1, that would be just, well, I guess we could just put it in. Let's go ahead and simplify. 10 minus 0, so I just took care of the denominator all in one big step there. And then just like the other one, so average rate of change, it's pretty procedural where we say, all right, well, I need this. So I need to find A of 10. So A of T2 is finding A of 10, which is doing 5,000 E to the 0.012 times 10. Okay, so this is going to need a calculator. All right, so let me get that going. Okay, so I'm just going to back it up. There's my scientific calculator. Okay, so I'm just going to plug that in. So we have 5,000. Okay, and then E, you could just type in E at the keyboard. E, it knows what it is. And then we need to raise it. So use the b, and then I'm going to use parentheses to be safe, the 0.012 times 10, and then parentheses. Okay, so we get that, 5,637.48. Okay, so that was the blue one, 5,637.48. Okay, so that, let me cloud that. There we go. Okay, so that's a t of 2. Yeah, the little t of little 2, I mean. And then we got that value. Okay, so that would go here. So 5,730. Oops, not 5,000. I saw the 7 wrong. Let me make it so I have a little more room too. Okay, so that is 5,637.48. And then we'll need the minus. So probably should have given myself a little bit more room. Sorry. I think we'll be okay though. And then I need to do the T1 value. So A of T1 is A of 0, which is 5,000 e to the 0.012 times 0. Well, that would simplify to be 5,000 e to the 0. And then if we know certain rules, remember that b to the 0 is 1. Okay, so a base to the 0 is 1, as long as that base is not 0. So that base can't be 0, but that's a very rare case. So a base to the 0 is 1, as long as the base is not 0. So that means 5,000 times 1 is just 5,000. And we could have plugged that into the calculator to verify. It definitely is 5,000. So we would minus 5,000 from that, which means we're left with 637.48. And then, well, if we divide and round, so I'm just going to take, where's my calculator? I'm going to show. Okay, so, and you could use this where it kind of knows what it's going to happen if you push. Oops, never mind, sorry. Let me change that. Let me click on there. Okay, so I want to do the answer minus the 5,000 that we have. Enter to get this. And then I want to do my answer divided by 10 to get that. And then to 2 decimals, it would be 63.75. 63.75. Okay, and I'm going to box it, but let's make sense out of this. So I kind of took all the space, but I can fit it right here. Okay, so it says find the average rate of change per year of the total amounts in the account for the first 10 years of the investment. All right, so what this is saying for us is over the 10 years, so this is a dollar amount because these are dollars up top. So you have dollar amounts up top times in years. So we have dollars per years. This is a positive value. So what we would say is the average rate of change increases by 63.75. I guess the dollars would go over there. Let me erase that. So the dollars is left of the number, so like that. So the average rate of change increases by $63.75 per year. That's what it's stating. So that's how the account changes. So it's like every year you get 63 new dollars in this account based on this interest rate. Okay, and that's true for the first 10 years. So if you change it to a different amount of years, we would get a different average rate of change. Okay, so it depends. So the longer it would be, the higher it would go, because that's how banking works. Okay, anyway, so that's it. So that's a application of it. So hopefully it makes a little sense. And we said it increases because this is positive. I mean, we could see the amount, the amount here in the blue was after 10 years. So 5,000 increased to the 5,600. Okay, and then we're just changing it into an average because of the 10 years. Okay, so that's that. Well, if you do have any questions, please let me know. Otherwise, thank you for watching, and I will see you next time.